We go through Regents Prep 1. We start with a short constructed response. So we're going to base our answer on the information below. It says, in the modern model of the atom, which atom is composed of three major subatomic or fundamental particles? So I want to think, okay, subatomic particles. Name the subatomic particles contained in the nucleus. Well, first, subatomic particles would be our protons, our neutrons, or our electrons. So, who's in the nucleus is just my protons and neutrons. So, there's my answer there. State the charge associated with each type of subatomic particle contained in the nucleus. So the charge of only who is in the nucleus. So we said protons and neutrons were in the nucleus. So our protons are positive. And our neutrons are neutral. Or you could say 0. I want you to be careful that you do not say that the electrons are negative because it said only what's in the nucleus. So now we say, okay, what is the net charge of the nucleus? So I want you to think net charge. I want you to always give them the actual charge, so positive, negative, or neutral. And net, I want you to give them the number. So net is the number. So the net charge of the nucleus, and that's if I can. So overall, I have protons and I have neutrons. So my protons are positive, neutrons are neutral. Overall, positive. Number 1, A, B, and C are done. Number 2, base your answer on the electron configuration table below. So we have our electron configurations. Which electron configuration represents the excited state of a calcium? So excited of a calcium. So first I think we should go to our reference table and we should look up the electron configuration of the regular calcium atom. So let's see here. We see Ca is 2A82. So I'm going to write that down. Now that is going to be its ground state electron configuration. So they want excited. So I have to move them, but I don't want any extra or any less. So here I like this 2873 because I still have exactly 20 electrons, but I moved them. The one from here jumped up to there. So the answer to this one, I'm going to write it over here, would be element Y. Or you could tell them 2873. Actually, you should probably say that. 2873. Boom. 3, base your answer on the data table. We have our isotopes of neon. So it says, based on the natural abundances, the average atomic mass of neon is closest to which whole number? Well, if I'm thinking about the whole number, I'm going to look at my percent abundances. Here I see 90.9 is my highest percent abundance. I'm going to look at the mass, 19.99. Well, if I round that to a whole number, I would put 20 as my answer. So most abundant is always going to be closest to that whole number. And then it says show the correct numerical setup for calculating the average atomic mass. So they only want the setup, so I don't actually have to solve it. So what I'm going to do, I'm going to take my atomic mass, and I'm going to multiply it by my percent abundance, only I don't want it as a percent. I want to change this to a decimal abundance. And to do that, I'm going to divide by 100. Or really, that moves the decimal place twice, so I'd move it over twice. So I'm going to multiply those all together, and then I'm going to add them. So I have 19.99 times 0.909, mass times my decimal abundance, plus I have 20.99 times 0.003 plus, I'm going to write it on the next line, I am 21.99 times 0.088. So always put those in parentheses so you know that you're multiplying them first and then you're adding them all together. So it's the sum. Okay, so an atom has an atomic number of 9, a mass number of 19, and an electron configuration of 261. Explain why the number of electrons in the second and third shell show that this atom is in an excited state. So I want to kind of look here and see that it says 261. So remember that 8 can fit in the second shell. So it really should say, if I was going to do this, instead of 261, really I'd even go 27. That would be, if I look on my reference table, I'm not going to find a 261. So that means it's excited. So what I would say is that the second shell is not full before an electron goes in the third shell. So second shell not completed with 8 electrons before electrons are in your third shell. Something like that. You have to word it exactly like that, but basically the second shell is not full. So 5 says base our answer on the Balmer series. So it refers to the visible bright lines in the spectrum produced by hydrogen atoms. The Coulomb wavelength of each line in this series is given in the accompanying table. So let's see. Explain in terms of both subatomic particles and energy states how the Balmer series is produced. So in terms of both particles and energy, so I have to say both, Balmer series, I want you to think, it said it was visible bright lines. So essentially, it's light. They're asking me how I make light. Well, I make light when my electron starts in my ground state. It goes up to my excited state. It's going to gain energy. Then the electron's going to fall back down and release energy, going back to the ground state. So I want to say something about that absorbing and the releasing energy because of the energy states. And I want to make sure that it's the electron that I'm talking about. So I'd say the electron releases energy as it falls back to the ground state. I would focus on the fact that that electron releases energy. That's really what I'm going to look for in your answer, but you're also giving them a more clear picture. So 6, an atom in the excited state has an electron configuration of 272. Explain in terms of subatomic particles, that's important, why this excited atom is electrically neutral. So they told me that up here that it was in an atom. Well, anytime that I have an atom, my protons equal my electrons. Every time. So it's going to be electrically neutral because protons are positive and electrons are negative. 7. Base your answer on the information below. An atom in the excited state has a configuration of 272. Write the electron configuration of this atom in the ground state. So if I want to go back to the ground state, my electron configuration, I'm going to make sure that I got to fill my second shell first. So instead I'm going to take one of these electrons from the second and a little bit back into my, third shell back into my second shell. So I'm going to go 2, 8, and then one of them moved, so it would just be 2, 8, 1. I could go to my reference table and verify that that is a ground state if I wanted to on the periodic table. 8 8. In terms of protons and neutrons, why U-235 and U-238 are different isotopes of uranium. So protons and neutrons, why are they different? So if they're isotopes, you're going to have the same protons and you're going to have different neutrons. Always. You guys have been really good with that in class, so hopefully that's good for you. The isotopes, always same protons, different neutrons, because they have the same atomic number and different mass. Okay, number 9. I have a bright line spectra. You've seen pictures like this before. It says identify all elements in the mixture. So I'm going to go see where my lines actually match up. And I can do this quickly by looking and saying, well, I don't have anything. Oops, hold on here. Sorry, I thought I was talking to her, but I'm actually talking to you. So identify all the elements. If it's not in the mixture down here, but I see a line up here, like this cadmium, that doesn't match. So that's not in it. So cadmium's not in it. I'm going to look and make sure. Let's see that lithium's line match. So I go up this line, we'll go up here. Actually, I'll just do all the lines. Let's see. Okay, looks like I covered up pretty much all. Sorry, I don't draw very straight lines. I'm sure you're better at this. But lithium's lines are all covered up, strontium's lines are all covered up, and all these where I'm hanging out with my cadmium makes it not in it. So to identify the elements, I'm going to say it's lithium and cadmium. Nope, no, I just said that wasn't in it. Lithium and strontium. Okay, explain in terms of both subatomic particles and energy states how the bright line spectrum is produced. So again, they're talking about, well, how do I make light? So bright line spectrum is always just light. So remember that. So I make light. Again, my electron has to absorb energy and go into the excited state and then release energy and go to the back to the ground state. So this one already a little different than before. We'll say the whole thing. So we'll say electrons absorb energy and move to the excited state. Then they release energy, which is the important part. When falling back to the ground state. You do not have to write all that. It's a very complete picture of how I make light. Again, what I underline, the fact that the electrons release energy, that's what's important. I don't make the light until I release. Okay, so nice view of my table. Okay, 10. We're in the electron configuration for an atom of aluminum-27 in the excited state. So, okay, I'm going to focus on this fact that it's aluminum. They want an electron configuration. So I'm going to go to my reference table, and I'm going to say, okay, I have aluminum right there. I see that it is 283. So normally it is 283. So if I now want it to be excited, I have to move one electron from my second to my third shell. So I go with 2, 7, 4. That is not the only answer, but it's always easiest to slot it from the second to the last shell into the last, or to make a new shell. 11, base your answer on the accompanying table. What is the total number of electrons in an atom of Cu65? So Cu65 was right here. If they want the electrons, Well, I'm going to think, well, my electrons are actually, they equal my protons. And they didn't tell me my protons. So actually, I should go to my reference table. I'm going to find Cu. I see it's right there. It is atomic number 29, so that is my number of protons. So my electrons, that's exactly it. 29 electrons. So they say, okay, in B, they want to show the correct numerical setup for calculating the atomic mass. Remember that your atomic mass is always calculated. It's going to be your percent natural abundance, but as a decimal, times your atomic mass, and you're going to add those together. So I have, let's see here, 69.17. Oops, sorry, that's my percent. So 0.6917. I'm dividing that by 100. So 0.6917 times 62.930 plus 0.3083 times 64.928. So I'm just dividing my percent abundances by 100 to move that decimal. And I add them together, and I just need the setup, so I'm done. 12, compare the mass of a proton to the mass of an electron. Well, I should mention both. A proton is going to have the mass of 1 AMU, as will a neutron, by the way, and an electron will have a mass of 0 AMU. Or you could say that a proton is more massive than an electron. I'd also let you say that. Either answer. Okay, multiple choice. So 1, compared to a sodium atom in the ground state, a sodium atom in the excited state must have. So if I'm considering just the excited state to the ground state, I'm not going to have a greater number or a smaller number of electrons. Those just aren't going to be true. I'm going to have the same number of electrons. So am I going to have electrons with greater energy or an electron with less energy? Well, if I'm excited, I absorb energy. So excited state, absorb. So I'm going to pick choice 3. Number 2, which particles are isotopes of each other? So if I'm an isotope, I have to have the same protons, so same protons, and I have to have different neutrons, which actually means that I'm going to have a different mass. So remember, mass number is the top number. Your protons are your bottom number, so they're both 1s. I like that. 1 and a 2. I don't like that. 1 and a 2. I don't like that. 1 and a 2. I don't like that. Those both have the atomic number of 1. They have a different mass number. Your mass number is on top, so I pick choice 1. 3, in Rutherford's gold foil experiment, some alpha particles were deflected from their original pass, but most passed through the foil with no deflection. Which statement about gold atoms is supported by these experimental observations? Number 1, gold atoms consist of mainly empty space. Yep, I like that. In the Rutherford, that most passed through, that's what gives me that mostly empty space. You want to make sure you also know that it gave you a dense positive nucleus as well. Okay, number 4. The characteristic bright line spectrum of an element occurs. So bright line spectrum, I think that's light. When does that occur? When they move from lower to higher? Nope, I gotta calm that down. So move from higher to lower. When they're lost or when they're gained? I hate that lost and gained. They will have the same number. So I like choice 2. They're gonna move from higher to lower energy levels, and they're gonna release energy in the form of light. 5, the modern model of the atom shows that electrons are they orbiting in fixed paths found in regions called orbitals? Ooh, I think I like that. Modern model. I don't like the fixed paths. I don't like that the electrons are combined with the neutrons in the nucleus, and they're located in a solid sphere covering the nucleus. Yeah, I just don't think that sounds right. So regions called orbitals are where your electrons are. Okay, number 6. The atomic mass of an element is calculated using the, so we were just doing things like this, it's going to be a weighted average. That's why we're multiplying by that decimal abundance and by the mass and then adding them together. So the atomic number ratios of the naturally occurring, I like that. No, I don't. I don't like the atomic number, actually. So atomic number and the half-lives. Oh, we're just starting to do nuclear. Nope, I don't like that. 3, masses and the ratios of the naturally occurring. Yeah, I like that masses or the masses and the half-lives. Nope, so I like choice 3. It is the masses times the ratios of the naturally occurring isotopes. 7, the modern model the atom is based on. Well, was it one scientist or many scientists? It was going to be many scientists, so not one. And over a short period of time or a long period, a very, very long period of time. We had to do work from, remember, we had Mendeleev, we had Dalton, we had Bohr, Rutherford. So we could keep going. So that was a lot of different scientists, long period of time. 8, how many electrons are contained in the Au plus 3 ion? So I'm going to go ahead and I'm going to go to my periodic table and I'm going to look up Au. So Au number 79. So it would normally have 79 electrons. So, but that plus 3 actually means I lose 3. So 79 minus 3 is going to give me 76. So I choose 1. Number 9, which electron configuration represents the electrons in an atom of the excited state? So if it's excited, it's not going to be on the periodic table. So I can just check. I'm going to find a 2,4, a 2,6. Actually, let's prove it. Excuse me. 2,4. 2,4 is carbon. 2,6 is oxygen. 2,7,2 is magnesium. Nope, that's 2,8,2. Ooh, maybe it's that. Oh, 2,8,2 is magnesium. So 2,7,2 wins. Carbon, oxygen, magnesium. Not on the periodic table. Number 10, which two notations represent an atom that are isotopes of the same element? So, well, first I have to be the same element. So that says O and F, that's Cl and K. So they're not the same element. So they're out. So here I have both SN, so I think they have to have the same atomic number, which they do, but a different mass number. So if I look at choice 2, they actually have the same mass. So I need it to be different. I like choice 1. Got the different mass. 11, atoms of different isotopes of the same element differing their total number of. So we just said that they're going to have different number of mass, so that's going to give us a different neutrons. Oh. This is hard even for me to read, so sorry about that. But which model correctly describes the location of the protons and electrons in the wave mechanical model? So I want to think, okay, wave mechanical, what does that mean? Well, wave mechanical was modern. So where the heck were the electrons in the modern model? So in the modern model, were they in the nucleus? No, definitely not. So dispersed throughout the atom, I like that. Oh, wait a second. There are protons and electrons. Silly. So I actually do like in the nucleus for my protons. I like those. And I'm looking at my electrons. Do I want specific shells or region of the most probable electron location? So I don't like the specific shells. So actually I do get rid of A, which is going to leave me, I do like that, and I do like that they're in the nucleus. Sorry, I previously crossed that out. So I like B. See, that's why I always got to pay attention. Even if you know what you're doing, you can mess up. 13, what is the total charge of the nucleus in a carbon atom? So total charge of my nucleus. Remember that it has protons and neutrons in it. And if I'm thinking about my protons and neutrons, neutrons are neutral, so they don't really count. So I really care about my protons. I know that it's carbon, and carbon has 6 protons, so plus 6. 14, which two particles each have a mass approximately equal to 1 atomic mass unit? So let's see, 1 atomic mass unit. Well, electrons have no mass, so it's my protons and it's my neutrons. So I'm going to get rid of this electron here. Proton, electron, nope. Choice 4, proton and neutron. 15, compared to an electron in the first electron shell, an electron in the third shell, so comparing first to third, the same atom has, so the third shell, does it have more mass? Nope. Or less mass? No. Same mass, which really is barely anything. Nothing. For all intents and purposes. So, okay, less energy or more energy? Well, I moved up to the third. I have more energy. More energy further from the nucleus. 16. An atom in the ground state contains a total of 5 electrons, 5 protons, and 5 neutrons. Which Lewis electron dot represents the atom? Well, remember that your Lewis dot is going to be based on your electron, so I want to kind of focus there. But remember that your Lewis dot is going to be your valence electrons. That's going to be important. So my valence. So if I have 5 electrons and 5 protons, I'm going to go here and I'm going to actually look. If you have 5, your boron, which has a configuration of 2,3. So if it's 2-3, those are your valence, just 3. So I like choice 3. Don't get tricked, that one's a little tricky. Number 17, what is the total number of electrons in an atom of potassium? So it's potassium and it's an atom. So in an atom, your electrons are the same as the protons. So I'm going to go to my periodic table. And I'm going to say, okay, well, let me see if it's the same as the protons. K has 19 protons. So it has 19 electrons. 18, which was a direct result of the gold foil experiment. So gold foil, you want to remember that I have the mostly empty space in my positively charged nucleus. So I like choice 1, and I remember that that is Rutherford. "19. The wave mechanical model of the atom is required to explain the." So remember, again, wave mechanical is modern. So I'm going to explain this via the answer. So the spectra of elements within multi-electron atoms, it's because it wasn't until the modern model of the atom that we knew how the electrons could move and what they did when they make light. So basically, because the electrons move to make light, I like choice 4. Remember, they're in orbitals. 20. Which subatomic particle is located in the nucleus of a carbon atom? So just remember that's carbon. What's in the nucleus? Is it just protons? No. Is it just neutrons? No. Is it protons and neutrons? Yes. Is it protons and electrons? No way. Electrons are outside. 41. The total number of protons, electrons, and neutrons in each of the 4 atoms are shown. Which 2 atoms are isotopes of the same element? So remember, isotopes have to have the same protons. So here, I have 6 protons, 7, and 8. So I like the 6 protons. And my number of electrons, I don't really care about. With my number of neutrons, 7 and 8, that's also, I need this to be different. And this to be the same. So it's A and B, choice 1. 22. Atomic masses, they give it to us in the table. They talk about naturally occurring isotopes. That should kind of point you in the right direction. So which setup can we use to determine the atomic mass? Remember, atomic mass is that weighted average. So I'm going to take my atomic mass and I'm going to multiply it by my natural abundances, but I'm going to change those from a percent to a decimal. So here I get boom, boom, and move over twice, 0.075, 0.925. So 6.02 times 0.075, 0.702 times 0.295. I like choice 1. 23. What is the overall charge of an ion that has 12 protons, 10 electrons, and 14 neutrons? So you don't really care about your neutrons because they're neutral, but 12 protons means you're plus 12, and 10 electrons means you're minus 10. So if you just figure that out, you're overall plus 2. So I like choice 2. 24. Compared to the charge of a proton, the charge of an electron has. So we're going to first think about the sign, because I think that's easier for you guys. So protons are going to be positive, and electrons are negative. So the same sign, nope. Opposite sign, yes. Same sign, no. So it's not 1, it's not 3. Now I want to think about a greater magnitude or the same magnitude. So if I said, well, what's 1 proton? You would tell me it's plus 1. And what is the charge of 1 electron? You would tell me it's minus 1. So that means they have the same magnitude. So same magnitude, opposite sign. Okay, sorry, getting there. 25. The mass of a proton is approximately equal to. So again, I want to think I need to know my proton has the mass of 1 atomic mass unit. So 1 atomic mass unit. Always going to be the mass. Which electron shell contains the valence electrons of radium in the ground state? Well, I should think, well, who the heck is radium? So I can go to my table S if I need that. I can also notice that radium is Ra. So I see this electron configuration here. Notice there's a dash before the 18. That means I didn't write the whole thing. So you're better going out to your period to see that there are 7 shells. The period number will always give you the amount of shells that you have. So the valence electron, 7th shell, is about Ra. 27. Subatomic particles can usually pass undeflected through an atom because the volume of the atom is composed of largely empty space. Remember that this came from Rutherford. His gold foil found us the most empty space. 28. The nucleus of an atom of cobalt-58 contained. So they want to know, well, how many protons and how many neutrons? Well, I should go, if I want to know my protons, I have to go to my periodic table. Cobalt has 27 protons, so I like 27, so I'm going to get rid of choice 3 and 4. And now I just want to think about my neutrons, so all I have to do, I'm going to take 58 and I'm going to subtract that 27. So if I do that, I'm going to get 31. So I have choice 1. 29. Which statement best describes the nucleus of an aluminum atom? So I'm going to think, okay, well, how many protons does it have? Aluminum has 13 protons. So it has a charge of plus 13. So I don't like this negative 13 or this negative 13. So 3 and 4 are out. And it's surrounded by 10 electrons. It's surrounded by 13 electrons. Well, if it's an atom, it has 13 protons. So also it says 13 electrons. So it's choice 2. Atoms or protons equals your electrons. Alright, question 30. What is the total mass of the smallest? So is it the mass of 2 electrons? Well, that'd be about 0. The mass of 2 neutrons, that'd be about 2. Mass of 1 electron plus the 1 proton, well, that'd be 1. Mass of 1 neutron plus mass of 1 electron, well, that'd be 1. So about the smallest, it's choice 1. Electrons, you can think of it as a mass of 0. They'd be like a tiny, tiny, tiny one, but 0. 31. What's the total number of protons in an atom with an electron configuration of 2, 8, 18, 32, 18, 1? Well, I can go ahead and look that up if I want, so I can see what atomic number it matches up to. And if I go here, 2, 8, 18, 18, 1, that's not it. Maybe it's a U. Oh, I got a dash. Oops, sorry, that's 47. So dash 18, 32, 18, 1. I mean, there's something in front of the dash, so I go see, well, what the heck was in front of the something? 2, 8. So I like that. Or add the electrons. That's the answer to. 32. An electron in a sodium atom moves from the third shell to the fourth shell. The change is the result of, well, does it absorb energy or release? Because it does not gain or lose. Definitely not. It just moves. So if I go to third to fourth, I absorb. I got excited. 33. I'm going to look at the bright line spectrum. What elements are present in the mixture? Well, remember, if I'm in the mixture, I also have to be in all the lines up here. So I can immediately see G's not in it because I don't have that line. And if I check all of these, I will see, yep, it's going to match up with D and E. So I have to use it and feel like you're all the way out, but all of those match. E and D only. 34. In the late 1800s, experiments using the cathode ray tubes led to the discovery of cathode ray tubes. I want to think that was J.J. Thomson. He made his plum pudding from that because he found the electron. He found the electron. All right, we're almost there. 4 questions. We can do it. This one was a long one. One of the longest ones that we have. So 35. The atomic mass of titanium is 47.88. The atomic mass represents the, well, let's kind of look at our choices. Is it the total mass of everything in the whole atom? Total mass of the protons, neutrons, and the electrons in the atom? Is it the weighted average? Ooh, I think I like that. I see decimals. You see decimals go with weighted average. And is it the naturally occurring or the most abundant? Nope, not most abundant. Naturally occurring. I like choice 4. 36. Which electron configuration represents an atom of magnesium in the excited state? So magnesium, I think it's Mg. If I look it up on the reference table, I get 282. So I want it to be basically the same electron configuration I want to move. So I like choice 1, 273. Same number, but they move. 37. Compared to an atom of hydrogen in the ground state, an atom of hydrogen in the excited state has, so if I'm excited, I absorb energy. If I go back to the ground, I'll release it. So I make light, I am absorbing and then releasing. But here, I just got excited, so absorb. 38. What is the total number of electrons in the outermost shell of a phosphorus atom? So if I'm in the outermost shell, they're asking me about my valence electrons. So I would just go and say, okay, phosphorus, 285, so there's 5 valence electrons. So it's choice 4. That brings us to the end of Regents Prep 1. I hope that helps. You guys are going to do awesome on the Regents. See you soon.